Hello, so in this video we're going to start the next chapter and we're going to be looking at stochastic calculus, okay? Now I have kind of alluded to stochastic calculus before, kind of, how we kind of differentiate Brownian motion, for example. We said, I've kind of shown you that because Brownian motion is a fractal, basically, if we zoom in an infinite number of times, it will still be this kind of jagged movement. Whereas you see, normally, if we differentiate something, we've got a curve, say, well, if we zoom in enough, we effectively get a straight line. And of course, we know how to find the gradient of a straight line. So in other words, what we say is that, we can find the gradient at a particular point. Of course, the gradient at different points will be different. Okay, but here, no matter how many times we zoom in, we end up with this jagged movement. So it means that differentiation is impossible because we can't find the gradient of a straight line. We can't find the gradient of this jagged line. It never becomes straight. Okay, so really, this is where stochastic calculus comes in, and it's just basically ordinary calculus. Okay, but it includes the randomness element. Okay, so let me kind of show you what I mean by that. You've already seen this before. So I'll show you using the example that we have before. So here we go. Okay. Now, if we had, the share price is given by the initial share price. So the share price at a time t is given by the initial share price times by some growth rate, and that's an exponential growth rate. Okay, which changes over time, and the rate is given by r. Okay, so we have st equals s naught e to the rt. So if this is st, okay, and this is t, all right, then we start at s naught, okay, and we follow this kind of exponential growth. And we can differentiate that using normal calculus. Okay, we can basically say that the derivative of our share price with respect to t, okay, will be given by, well, what's basically the derivative of this? Well, the derivative of this is going to be, we have s naught, okay, e to the rt. It's an exponential function, so it's just going to be the, s naught is just a constant, okay, so it's just going to be the derivative of rt multiplied by all of this. So the derivative of rt with respect to t is going to be, what's it going to be? It's going to be r. So we end up with r s naught e to the rt. Yeah, you happy that that is just the derivative of that? Okay, basically what we're asking is the derivative. Say, for example, you have the derivative with respect to x of e to the function of x, okay, or even just a constant times e to the function of x. Well, that's just going to be the same thing multiplied by the derivative of this power. Yep, so the derivative of that function. So that's all that's going on there. So that's all I'm doing down here. So basically I can say that, the derivative of my share price is r e to the s naught e to the rt. But look what s naught e to the rt is. That is that there, which is st. So I can just rewrite this as r times my share price. So my rate times my share price. Okay, okay. So this is what I would do using normal calculus. But of course, I've said that now, a share price normally models not this kind of growth rate. I mean, this is kind of a good model for kind of showing how the share price changes. It's an exponential growth rate, right? But it's this thing. It's s naught e to the rt. Okay, but we have to include Brownian motion into it. So in other words, this is still st against t. Okay, and it follows the same kind of shape. As that, but this time we have Brownian motion added, and we say that it's Brownian motion. Okay, and we can have any constant times Brownian motion. And actually, I've talked about that constant beta before with the Brownian motion. It's really, really difficult to find. And actually, there's whole sections of the industry, whole divisions of the industry that are devoted to trying to find out what that beta is. Okay, but it's beyond the scope of this course. I just want you to be aware of that. Okay, so essentially what this term does, it just accounts for the randomness. So basically we have this kind of random pattern, and this is kind of your familiar Brownian motion that's happening. Okay, so here we go. It's going to look like that. So this is what the beta t term is doing. It's kind of adding the Brownian motion, if you like. Well, obviously trying to differentiate this Brownian motion, okay, is going to be much more difficult, and therefore this is where stochastic calculus comes in. Okay, so it's random, but it's not too random. It does still follow some kind of pattern. Which allows us to use stochastic calculus. So basically what I'm talking about is this thing here. Okay, I've said it's random. Well, it is random, but it's randomness that comes from something within, is how the share price moves, effectively. So it does have some kind of distribution that can be found using stochastic calculus. So in other words, now what I'm saying is that if I want to find the derivative with respect to t of this thing up here, so this thing up here, let's see if we can get that in frame, there we go, then this will be equal to the same thing that we had before, so r, or no, actually, wait. If I try and differentiate it using ordinary calculus, right, I'm going to have to use, if I try and differentiate using ordinary calculus, as it turns out, it doesn't have any meaning, but let's try and do it anyway. So say, for example, if I could differentiate this using the ordinary calculus, what would I end up with? Well, it would be, it would be S naught, it's basically what I'm saying is that derivative, it's this multiplied by the derivative of this power. So in other words, what I'm saying is it's going to be S naught e to the RT plus beta bt, okay, multiplied by the derivative of this power, okay, multiplied by the derivative of this power. So the derivative of this power would be RT, so the derivative of RT would be R, okay, plus the derivative of this beta bt, yeah? So this beta bt, derivative of that with respect to t, that's going to be, what's it going to be? It's going to be dbt, the derivative of bt with respect to time, okay? Multiplied by beta, is that right? Yeah, multiplied by beta, so let's see if I can squeeze a beta in there. Multiplied by beta, so add those two things together. Okay, fair enough. Let's now try and well, that's basically what this is saying now. Is this here? You're happy that this is just my st? Yeah, it's just my st. It's just that. Okay, so this is now r plus beta dbt by dt. So the derivative of Brownian motion multiplied by my share price st. Okay, so this is what we end up with. And actually, I could probably expand that out. So r st plus beta dbt by dt, and I'm just going to stick the st at the front there, so st there. So this is what I end up with. But basically, this is where the problem comes in, because what is the derivative of Brownian motion? Well, that's where the problem comes. Okay. Now, I'm just going to introduce something new now, so it doesn't come as too much of a shock later on. Or I don't mean it's shock, but I just mean so it's not brand new later on. At least you're familiar with it. I'm going to introduce this idea of what's known as differential form. Well, differential form is basically rewriting this thing. So it's just, well, let me show you what it is, and then kind of hopefully you can see what's happening. So, right, dst effectively this is. Should have just kept the t in there. dst with respect to t, so I'm just going to rewrite it out first of all, equals rst, just equal to that thing, right? Well, what differential form is it's basically writing it in such a way. It's a bit like when we're doing separation of variables for ODEs. If you kind of go back and watch my ODEs variables, basically what we try and do is we treat this as a fraction. And we get everything involving, and we just basically multiply through by dt. So in other words, it makes the integration. We can kind of integrate it then. It's a bit like separation of variables. So in other words, what I'm saying is that we just have dst still here by dt. If I just multiply through by this dt, effectively, and write it like this. This is what's known as differential form, because it kind of makes, hopefully you can see that, it kind of links to the integration, okay, like that, okay. So now let's try and get this thing here into differential form. So we end up with, this is the differential form for the ordinary calculus case. This is dst by dt equals rst plus beta st times the derivative of Brownian motion with respect to time. Okay, so that implies that therefore we end up with dst, so just multiply through by dt, is equal to rst dt plus beta st dbt over dt multiplied by dt. Okay, so are you happy that those two dt's just effectively cancel out? So then this is what we're effectively left with. But again, we've still got this problem, is what is the derivative of d beta by dt? And this is actually really useful because we can use something known as Ito's lemma that looks at this. Okay, so we'll look at this in a little bit more detail in just a second. Okay, but in actual fact, because we don't know what the derivative of this is, then we can't actually use differential calculus. So what I've just written down here, what I've written down here, or what I've written down here, they're the same thing. What I've written down there doesn't actually have a lot of meaning. Doesn't have a lot of meaning in the kind of ordinary calculus sense, because we don't know what the derivative of Brownian motion is, or we can't differentiate Brownian motion because of this thing. Basically, if we zoom into it, if we zoom in on it, infinite amount of times, it's still going to be jagged. So we can't differentiate jaggedness. It doesn't go straight. So yeah, hopefully that makes a bit of sense. But essentially, yeah. So I've introduced now, just in this term, I've introduced the difference between ordinary calculus and the reason why we want to use stochastic calculus. Hopefully that's kind of clear in your head. It's because of this Brownian motion. Okay. And I've kind of hopefully shown you that how these two things link together, and what we would do if we were differentiating that thing. That's nice and easy. We can do that. But this thing doesn't have a lot of meaning because of this term here, the derivative of Brownian motion. Okay. So basically, what we're going to do. Normally when you teach calculus, you teach differentiation first. Okay. So when you're learning it on your A level, you teach differentiation first. Okay. And then from that, you lead on to integration. Okay, you lead on to integration. So you get the idea of differentiation first, okay? Then from that you lead on to integration. You see that integration can either be treated as something totally different to differentiation. Differentiation is finding the gradient, okay? Whereas integration is finding the area underneath the curve. Okay, differentiation is finding the gradient of a curve, right? So kind of you can see that they're two different things, but equally you can see that actually, by the fundamental law of calculus, or theorem of calculus, that they are actually inverse of each other. So if you differentiate something, you can always get back to that something by integrating. Well, usually you teach differentiation first, then you get integration. That's how it's kind of normally taught in school. Whereas with stochastic calculus, and in order to get the meaning, what we're going to do is we're going to start with integration, and then we're going to get the differentiation or the meaning of differentiation from stochastic calculus. Okay, so essentially we're going to start with integration, which is why I introduced this kind of differential form, because it just kind of makes differentiation easier. That's why we write it like that. It just makes differentiation or integration a lot easier. Okay, and then from that we're going to get differentiation. So this is really just an outlining video of what's going on.